Hello, welcome to this presentation on mixing temperatures. The goal of this presentation is to review electronic reset mixing valves versus thermostatic mixing valves and the differences in efficiency and comfort and life cycle cost between the two of them when we install them in a hydronic heating system. We will have a quick review, a little review of what outdoor reset controls are and what they do. Have a look at some of the Viessmann boilers and the reset controls that are on those devices, and a little bit of information on how to integrate reset mixing valves into our boilers. And I hope you find the information useful moving forward so that you can explain this information to the decision makers and install more of these electronic reset valves versus thermostatic mixing valves in your heating systems. So let's begin. Now, looking at why we put heating systems into buildings to begin with is to maintain a temperature inside as the temperature outside is getting cooler. If the temperature inside is changing as the temperature outside is changing, that's when occupants are going to become less comfortable. The idea here is if we add outdoor reset to our system, that temperature change is going to slow down. And as we slow down the changing temperatures inside, our bodies can acclimatize easier. That makes us more comfortable in the environment that we're in. The goal with outdoor reset really is to meter out the exact amount of energy that our building is losing and replacing it with that exact amount of energy to keep that temperature at a very consistent level. So we don't want to add too much heat or too much energy that's going to create an uncomfortable space, and we also can't deliver too little amount of energy that will also create an environment that is not comfortable. So the first thing is comfort. We add outdoor reset to maintain a better comfortable living environment in our spaces. A secondary reason that outdoor reset is desirable for your hydronic heating systems would be the energy savings that we achieve by using some sort of a reset control strategy on our systems. Almost a byproduct really of the comfort. So if we are metering out the precise amount of energy that is being lost by the building as it sits in an environment that's getting cooler outside, the occupants don't notice the difference inside as far as temperature changes because we're getting that exact amount of energy out there. The boiler is going to be operating more efficiently than if it was overshooting temperatures, adding more BTUs into the building than what's actually required. That impact also has an indirect result in the fact that you'll have less wear and tear on your heating equipment, so it's going to last longer in your buildings that are out there. Also, typically less maintenance would be required as the units are in operation over time. So you get the lowering cost of your fuel bills. You're going to burn less fossil fuels to heat your space and maintain that comfort level, and you're also going to gain a better operating heating system, so longer running, less maintenance, and just better performance overall. Just have a little look here at how outdoor reset actually works. You have your indoor temperature, which we're trying to maintain here. The objective is to maintain that constant temperature inside, even with all of the different activities that are happening inside. And generally speaking, how we achieve that is by zoning the heating system to make sure that we maintain comfortable living environments in each area or zone of that particular building. Meanwhile, outside, there are different changes happening outside. The temperature could be dropping. You could have sunny days versus cloudy days, windy wind conditions, and depending on how well your building envelope is, those can have some dramatic changes inside as well. What we know about the fact in physics is that hot goes to cold. So as the temperature outside is getting cooler, the building envelope has a specific amount of insulation, but there is going to be that draw of the indoor temperature being warmer, drawing through your building envelope to the outside. So hot's going to go to cold there. The amount of insulation that you have will slow that particular process down. So the more insulation you have in your ceilings and in your walls and in your floors, the less that heat is going to escape through those through the building envelope, but it just slows it down. So we still have to replace that amount of energy that we are basically transferring to the outside during our heating season. And the more the temperature changes outside, of course, the colder it gets, the more we're going to have to supply that energy to the building envelope. And using a hydronic heating system, water has an excellent ability to absorb energy and release it as we need it. So hydronic heating allows us to utilize that water to move that energy around the building and deliver it where we need it, when we need it, at the appropriate temperature to maintain that comfort level. And here you can actually see an outdoor reset, or what we call a heating curve, that we would utilize in a hydronic heating system. It's a pretty simple graph, really. On the bottom you would have your outdoor temperature, what we're dealing with, and an actual temperature outside. And when we use a heating curve, we can relate that outdoor temperature to a boiler supply temperature. So on the vertical you'll see different temperatures that the boiler would use as a set point, based on whatever the temperature is outside. So instead of a traditional type of heating system where we just have an on-off control, when you have a zone valve or a thermostat that's going to call for heat, and we hit the contacts on the boiler and it just maintains a specific temperature 365 days a year when that call is initiated. With outdoor reset, the system will first look at what the outdoor temperature is, and based on that, it's going to give the boiler a modulating set point. So as the temperature outside cools, the boiler is going to supply a hotter temperature to our building because the building is going to be losing heat at a faster rate. As the temperature outside warms up, we're going to slide down that heating curve, and the boiler set point is going to adjust to a lower supply temperature because the building is not losing as much heat if the temperature outside is warming up. So the outdoor reset control will utilize a specific curve, and based on that curve, the temperature outside will change the boiler supply water temperature at a different rate. We'll have a look at what those rates are here in a little bit. But this is a specific or basic outdoor heating curve, what they look like. We'll talk a bit more about the other values that you see on this, the outdoor design temperatures, etc., as we move through the little presentation here. But just enough to see what that control, or how an outdoor reset control works based on the outdoor temperature and supply temperature is here on this little graph. Now, how an outdoor reset control saves us energy by sliding up and down this particular scale and resetting that boiler supply temperature, there is a rule of thumb that is in hydronics. It basically states, we call it the 3-to-1 rule, but basically states for every 3 degree Fahrenheit, we lower that heating supply temperature. So as the boiler is dropping its supply temperature, for every 3 degrees that supply temperature drops, we decrease the amount of fuel consumption by, on average, of about 1% in operation. So there is a savings right there directly when we drop the supply water temperature going out to our heating systems. And that's the desire of outdoor reset. So we can do some dramatic heating system savings by following these heating curves and dramatically adjusting that supply temperature throughout the heating season. Not uncommon sometimes for boilers that have been utilizing on-off type of controls and have been retrofitted with outdoor reset controls to have 30 to 50% or more energy savings in comparison to previous operation with just holding a specific temperature 365 days a year. So this is the real desire of outdoor reset, is that As we mentioned, we're not changing our comfort. Our comfort is being maintained. That's the primary goal. But this energy savings and how we achieve it is another benefit of utilizing this outdoor reset. And regardless of the type of heating system that we use, so it kind of mentions here a condensing or non-condensing type of heating systems. We'll look at those in a little bit here because there is a bit of a difference between a condensing and non-condensing system. Regardless of the type of system you have here, this 3-to-1 rule would apply as far as your application. So there's a desire there, and we're going to kind of keep this 3-to-1 rule in mind as we start moving through outdoor reset and just talking about specific resetting of supply wire temperatures going out via mixing valves. So just remember this 3-to-1 rule as we move through the presentation. Now, previous slide talked about condensing boilers, and that's kind of been the style of boilers that we've been utilizing since the early 2000s, the wall mount style of boilers that you have in buildings. And these modulating condensing boilers replaced the non-condensing boilers of the years previous. The difference being that if you look at the graph to the right, your typical boilers would need to maintain non-condensing would need to maintain a specific temperature inside the boiler. They couldn't drop to below that little yellow line. So if the temperature inside of the boiler dropped below that particular level, inside of the boiler we would actually have condensation forming. So we would reach a particular point where the flue gas that's being generated when we have combustion, whether it's natural gas or propane in this case, when we get down below a certain threshold, the flue gas actually converts back into from a gas into a liquid, and we call that condensate in a boiler. And it's got a fairly high acidity level, and of course non-condensing boilers are not designed to handle that type of acidity in the condensate. Our newer condensing boilers that we have are designed with specific materials in mind as far as the construction of the boiler to handle that acidity of that condensate, and they are able to utilize the full reset curve here. So the yellow line where dew point you see on the graph, it's desirable for your condensing boilers to actually operate below that little line. That's where you actually achieve the efficiency on condensing boilers, is when the boiler actually gets to a condensing point. So that's where our goal is to utilize with a condensing boiler. It allows us to use the full outdoor reset curve here without having to worry about protecting the boiler from low return temperatures and that condensing effect on the flue gas when that temperature drops down below that yellow line. So just between a non-condensing and condensing boiler is the utilization of your heating curve. A non-condensing boiler can basically get to the point where it can drop down to the point where that flue gas still maintains itself as a gas and doesn't convert to a liquid. If we want to use the rest of the reset curve here, we'd actually have to add some sort of mixing devices in the system to throttle that temperature down and mix it down to a lower set point while still providing a higher temperature from the boiler. With a condensing boiler, there's no issue here. We can utilize full outdoor reset without any type of mixing devices in our system to protect the boiler from that condensing aspect. In this slide here, just looking at condensing boilers that we have down on the bottom right, we've got different product lines with Viessmann. You've got the 100 series boiler on the left-hand side. We've got the 200 series wall mount boilers. That's the second one from the left. We have combination boilers in Vitodens 200s. That's the taller boiler there, the Vitodens 222F. And then finally on the far right in the bottom is the high mass Vitocrossal 300 CU3A. So all of these particular boilers are condensing units, different controls. All of them are capable of outdoor reset operation. And the difference between why we'd want to have a condensing boiler on our heating systems versus non-condensing would be that energy savings that you get when we actually have a boiler in condensing operation. And the whole goal here, as you can see, is as we condense, the amount of that condensate coming out of the boiler directly relates to an amount of gas savings that we're dealing with. So basically, if you're looking at this during a typical operation of one of these condensing boilers that I just mentioned in your heating system, during a shoulder season when it's really not at design temperatures, which we're going to come to here in a minute, on average, if you measured the amount of condensate coming to your boiler, between 3 and 4 US gallons of condensate would equate to about 32,000 BTUs of energy that you have actually pulled back out of the flue gas, so it didn't go up your chimney and out to the atmosphere. It was actually pulled back into your heating system and used to heat your space. So that extra 32,000 BTUs every day compared to a non-condensing boiler would be the energy savings that you would realize from a condensing system versus non-condensing. If you were to look at the actual value of how much heat is actually in a cubic foot of gas, typically cubic foot of gas, it changes based on areas and the makeup of the natural gas, but on average you're dealing with about 1,000 BTUs per cubic foot in a cubic foot of natural gas. So directly related here, approximately about 32 cubic feet of gas every day is being saved. At a design temperature down below here, we see that we're dealing with about 22 gallons of condensate per day on that residential boiler, and that equates to about 178 cubic feet of gas per day of energy that we're recovering from the flue gas. So there is your energy savings, very simple to see in a condensing system. Directly relates to the amount of condensate that we're getting out of the boiler and the amount of gas that we're saving from having to be burnt to supply our space and maintain that comfort level in the building. So there's the desire to have that condensing boiler in your system versus a non-condensing, is that amount of energy that we can save every day when that boiler is in a condensing operation. I'll try to explain outdoor design temperature for you here on this particular slide. Basically, every heating system will start off, as far as sizing it, we'll start off with a set of plans for the building. The set of plans will include what the R values of the windows, the walls, the ceilings, etc. will be. So getting an idea of just how well that building is going to maintain heat as the temperature outside changes. And you're also going to need to know, based on that, where we're going to build that structure. This graph that we see here is for Toronto, Ontario, and you'll see the design temperature is minus 21 degrees C. And that's based on historical data from ASHRAE. So we use data or information that tells us the temperature outside to design a heating system in Toronto, Ontario would be minus 21 degrees C. If we don't design for minus 21 degrees C, if we design for something warmer than that, then obviously our boiler is going to be too small. So when it reaches minus 21 degrees C outside, you're not going to be able to heat the space. People inside aren't going to be comfortable. So that is the starting point, is what's the size and the R value of the building that we're building, and when we plunk that building down on a building site, where is that site at and how cold will it be at that particular site. Interesting that we design our boiler size for about 33 hours of actual outdoor temperature. But the importance of that, obviously, as I just mentioned, is comfort. So we have to maintain that living space at that consistent temperature inside, but our goalpost outside is continuously moving. So we have to make sure that we design for that coldest temperature. Even though about 3/4 of your heating season in Toronto is spent above 0 degrees C, we actually have a boiler big enough to supply and keep that temperature consistent down to about minus 21 degrees C. So this, looking at this, also gives you an idea that as the temperature outside is changing, there are huge benefits to comfort by sliding that temperature up and down that heating curve. With a condensing boiler, if we didn't have outdoor reset in this particular instance, our boiler would always be above our dew point temperature, which means the unit wouldn't be as efficient. So utilizing condensing boilers in outdoor reset, as the temperature outside warms up, this system would only not be condensing for about 3% of the heating season, where 97% of it you would actually realize a higher efficiency because we were getting that flue gas converting back into a liquid, and again we're grabbing those BTUs and putting them back in your heating system instead of them going up the chimney and out to the atmosphere. The importance here obviously is that as we look at our plans, we have to know where those buildings are. So part of the process here is every region will have a little bit of a different design temperature or a very large design temperature. And sometimes, depending on the region, the spread between the coldest temperature in the heating season and our point where we're not going to heat the space anymore can be quite wide. So the wider the spread between our design temperature and the temperature we don't need to supply heat to the building anymore, where it's warm enough, there is even more of an importance there to utilize that outdoor reset function, as we'll see here in a moment. And just for some examples, we looked at Toronto. We'll just go across Canada here and have a peek at the different temperatures that we're looking for and the different basically spreads between the indoor temperature and the outdoor temperature. And as I mentioned previously, the wider that spread, even the benefits of outdoor reset become even more important as far as our comfort level goes. So a little bit of a warmer design temperature for Halifax, -1 degree or 1 degree Fahrenheit, -17 degrees C would be the temperature that we would design our heating systems for if it's in the Halifax region. Here is Winnipeg, Manitoba. We see the outdoor design temperature when you're building here, quite a difference between the other two cities that we've looked at. We're at -34 degrees C. So about 24 hours of the heating season, we're at -34 C, but we are going to design that boiler to make sure the BTUs that it has available would be able to cover off when the temperature outside is as cold as -34 degrees. But if we look at that spread in comparison to the other cities we looked at as well, when the temperature warms up here, and there's such a difference between the warmest temperature in the heating season and the coldest temperature, that if we don't utilize outdoor reset, that temperature is going to be quite high. So as far as comfort goes, there's even more of a desire here and energy savings. The colder the design temperature is, to utilize that outdoor reset, to be able to utilize that heating curve to adjust that supply temperature as it warms up outside. And here's Edmonton, Alberta, same design temperature at -34 degrees C, just a slightly different profile as far as the amount of time spent in between the different temperature ranges. But same idea or concept here. We design for about 25 hours of the total heating season. So a large portion of our heating season is spent at much warmer temperatures outside, but that boiler is sized to make sure that we can supply the amount of energy needed at -34 degrees C. So you see the benefits here as the temperature outside warms up. If we're sliding that supply wire temperature down, we're going to realize a much more efficient and much more comfortable system throughout the heating season. And we see the design temperature in Vancouver is -9 degrees C on this graph. The temperature spread between the warmest temperature that we're still going to heat the building versus the coldest temperature that we need to heat the building at is much tighter here in Vancouver, but we're still heating or designing for a heat loss of our building at -9 degrees C, which we spend about 3% of the heating season in that range in Vancouver. More proof that utilizing outdoor reset to adjust that supply temperature will be beneficial to both energy savings as well as comfort in the building. And as the temperature outside is changing, as we looked at design temperatures at different regions and the amount of time spent at different temperature ranges throughout the heating year, inside we have possibly different styles of emitters, heat emitters that we would have in a building. And each one of those different types of emitters would require a different style of heating curve. They heat up at different rates, they release heat at different rates. So it's very, very difficult to supply one single temperature to multiple types of heat emitters and have a comfortable living space. So as we install our heating systems, usually if they're copper fin tube baseboard, you would have one heating curve for that type of baseboard system. A hydronic fan coil in a building would have another type of heating curve where it would move along a heating curve at a different rate. So as the temperature outside changes, we would need to supply a little different supply wire temperature to that and compare it to the baseboard possibly. And even more so when you get into medium temperature types of systems, cast iron rads, etc. When we try to couple those with higher temperature emitters, it can be a little bit of a problem and add some complexity to our system and some imbalance. So it's important, obviously, to not just know what the outdoor design temperature is when we're using outdoor reset, but also what type of heat emitter is in the building, because that will definitely influence the heating curve that we're going to use. And we'll have a look at that here in a moment to see how we can, what those heating curves will look like based on the different types of terminal units you see in front of you here. Important here, just as a note as well, is any manufacturer of an outdoor reset control, whether it's a boiler manufacturer like Viessmann or some other off-the-shelf outdoor reset control you're going to add to a system, there will be some very specific information on where that outdoor sensor should be located. And this is just cut and paste out of our manual. When you install the outdoor sensor, where we want to see it, the height in the building where it should be, the wall, whether it's what facing wall it is, north, south, east, west. We are very specific on which one is the best wall to install the outdoor sensor on. Obviously, the coldest wall is the best location for your outdoor sensor. Because that is going to be the coldest side of your building. And if we can maintain the heat in that side of the building, then we know that that supply temperature will be adequate for the rest of the building. So then basically, if we use one outdoor sensor for the whole building, that sensor should be on the coldest side of the building to pick up the coldest temperature. It shouldn't be in any areas where we are close to any type of influence from exhaust systems, for instance, your vent. So keep them away from your venting system, keep them away from any exhausts, vents on the side of buildings, whether they're bathroom exhausts or kitchen exhausts, etc. HRVs, all those types of things will give them a false sense of heat. Obviously, inside of the building is not a very appropriate area as well, so we want to make sure that we follow the guidelines in the manuals for these outdoor reset controls so that that sensor is sitting in the area that's going to pick up the best temperature to operate your heating system correctly. Here is an outdoor reset control, speaking of it in the previous slide. The control that is you purchase when you buy any of the 3 boilers that you see in this slide will have an outdoor reset control built into the actual boiler control. It has all the components when you purchase the boiler out of the box to install a proper outdoor reset system in your building. So we'll have a look at what those components are in the next slide. And the primary component that we need, as we looked at earlier, is the outdoor sensor. Each of the boilers that we saw previously in its installation package will have an outdoor air sensor, and that sensor should be obviously located in the area that is mentioned in the manual for proper operation. It wires into your control in the same spot on all 3 boilers, so we can see it here. And that is continuously feeding back information to your boiler control on what the temperature is outside so that your boiler can make the adjustments to the supply temperature in real time as the temperature outside is warming up or cooling down. It's modulating that supply temperature going out to whatever type of heat emitter that you've installed in your building. And on top of what you have out of the box, when you purchase a Viessmann boiler, whether it's a Vitodens 200 or a Vitocrossal 300, where that outdoor sensor is supplied and there's a heating curve that's available for you to adjust or reset your heating system, you can also add on components. And components that we make for these particular boilers, we have mixing valve controls available. So there's typically four components that you would have in a reset mixing valve. Clearly, we need a valve first, whether it's a four-way valve or three-way valve. For condensing boilers, Viessmann recommends three-way valves. They're more efficient in operation than a four-way valve. Four-way valve would be in a condensing boiler. So we've got the valve. We would need some sort of a temperature feedback to let us know what type of temperature is going out to those heat emitters. So we need a supply sensor that would come with the kit that we would supply, as well as a mixing valve module and a mixing valve actuator. So the supply sensor would connect to the mixing valve module. The mixing valve module would then connect to the mixing valve actuator, and the mixing valve actuator is installed on the mixing valve itself. And what will happen is, as the supply sensor feeds back temperature to the mixing valve module, that module will feed that temperature back to the control. If that supply temperature is too high, then the mixing valve module will have the actuator close off the supply port and reduce the supply wire temperature going out to our heat emitters. If that supply temperature sensor is feeding back to the mixing valve module and the temperature is too low, the mixing valve module will then in turn instruct the mixing valve actuator to open up the mixing valve to allow more or hotter water supply to our heat emitters to increase the supply temperature, so that we are metering out the specific amount of supply wire temperature based on our heating curve that we've utilized for that particular system. So it gives us a finer tuning of that supply temperature going out than even if we just had the boiler outdoor reset and one temperature. We'll have a look at that here in a moment. Here is a typical outdoor reset system. So we have a building here, and you see all three floors are high mass radiant heat. That makes it very simple for us to identify what heating curve we're going to look at to supply the right supply temperature to the building during the heating season. So you can see in the red here, we've picked the heating curve. So based on the outdoor air temperature, we are scheduling or modulating that supply temperature based on a 0.6 heating curve in this instance. So as the zones that are connected to this heating system open, they're all going to get the exact same supply wire temperature, regardless of the number of valves open, whether it's one or all of them or two or three. The supply temperature is going to be scheduled to give you the exact same temperature to all of those 9 zones that we have attached to the boiler. So is there a possibility of making this system actually work better? Is it possible to make it more comfortable or more efficient, particularly if we're using a condensing boiler in this application, by adding a mixing control strategy or mixing strategy here to this system? As we know, the boiler can, if it's condensing, can use the full reset scale here. We don't have to protect the boiler from low return wire temperatures as we would a non-condensing boiler. But in this particular application, your heating system is still working off of and influenced by the boiler temperature differential. So there's a built-in differential on your boilers, and that differential is meant to keep the boiler from short cycling, basically. So we want to keep the boiler operating at long run cycles, which makes it more efficient, so it runs for longer and it stays off for longer as well. So that's called a run cycle, when it's the time between the boiler firing to the time it basically stops firing and then restarts again. That cycle, we want to lengthen it out. The longer the run cycle, the more efficient your boiler is going to be. So instead of short choppy cycles where we have a boiler differential of 1 or 2 degrees, which would be very inefficient because the boiler would basically drop a degree or two, it would come back on, only heat up a degree or two, and then shut back off again. So oftentimes your boiler differential could be 8, 10, depends on the size of the boiler, could be greater than that as far as degrees Celsius. So you work off of an 8-degree differential, for instance. That would mean that your heating system is also going to operate off of that same 8-degree differential as far as operation. So we just looked at comfort, and those swings might get uncomfortable for the occupants as we move through here. If we add a mixing valve, and we throw in the mixing valve extension kit here, the module and the actuator, and we wire up the supply sensor here. Of course, the drive of the actuator to open and close the actuator from the mixing valve module, communication back to the boiler, and of course power the circulator here. That's basically makes up the how we install those modules. Now, instead of operating off of the boiler differential, we operate off of the differential on the mixing valve, so we can more precisely meter out that supply water temperature independent of the boiler differential. So as the boiler is in operation, we are metering out basically the precise amount of temperature we're looking for. As the boiler is off, we're doing the exact same thing. So using the mixing valve in this case would actually create a more comfortable environment for the occupants, as well as we would get an impact or benefit of a little bit longer run cycles on the boilers for more efficient operation. So even though we're using a condensing boiler and a one temperature system, there is still potential energy savings by utilizing a mixing device here to more closely meter out that supply temperature based on what we're really looking for as the temperature outside is changing. Looking at the Viessmann system, Viessmann boilers have the ability of adding on 2 of those mixing valve extension kits. So we have the ability of simultaneously supplying 3 different temperatures out to your heating system. So there's no priority here other than the highest temperature circuits getting its proper temperature. The other 2 circuits here use the mixing valves to meter that temperature back down so that we get precise amount of temperature supply water going out to those other terminal units that we're utilizing here. So you have the ability with your Viessmann system, depending on what you have there for terminal units, of really breaking that system up and feeding each one simultaneously the proper supply water temperature based on what we're looking for as the temperature outside changes. And this is how we can use those mixing valves, so adding mixing valves onto our system. As we add different types of heat emitters to our buildings, we want to meter out that heat at different rates to those different style of emitters. As we looked at earlier when we were looking at the different design temperatures for things like baseboard, cast iron, and high mass radiant heat, they have very different design temperatures, and the mixing valves will assist you in ensuring that we can match the correct heating curve to each one of those temperature requirements. So the first zone here, the red heating curve is 1.8, and that's the high temperature baseboard. Cast iron, higher mass, heavier as far as the metal or content in that as well. It's going to release heat a little slower. It absorbs heat at a different rate. So that heating curve is going to be a little bit lower. We add the mixing valve so that even though we're supplying the higher temperature to the baseboard, with the mixing valve on zone 2 here, we can effectively turn that temperature down to get the right supply temperature going out to our system. So at design, we want 76C for our baseboard, whereas we're only going to be metering out 61C to the cast iron rads at the exact same time if those zones are calling. And the third zone, which has a second mixing valve on it as our high mass radiant system, it's only going to require 44 degrees C water when we're sending out 76 degree water to our baseboard system. So again, much lower heating curve, 0.6, and a higher mass system means it absorbs more energy and it releases that energy over a slower rate, which means that it can utilize a much lower supply temperature and give us the correct comfortable environment we're looking for in our space. So with a Viessmann system, we have the ability of simultaneously giving you all 3 of these temperatures as far as design requirements, as well as sliding down all 3 of these curves as the temperature outside is warming up. So it gives us a large advantage on the comfort side of the system, and we're going to have a look at here on the efficiency side and energy savings, how we can utilize these to save some dollars for our homeowners as well. So we're going to design this system based on Vancouver Remember that the outdoor design temperature for Vancouver was about -9°C. We spent about 198 hours in that area, which is about 3% of the heating season. We need to basically make sure we have the boiler sized again appropriately for that coldest temperature of the year. We spend about 28, almost 29% of our heating season between about -2 and +5. Half the heating season is between 5 and 12 degrees C. And between 12 and 20, we spend about 18% of our heating season in that area. And with the mixing valves, we'll be able to, that are resetting, we'll be able to adjust that supply temperature completely throughout that whole heating season. And here we see an example of using the reset valves. All three of our temperature requirements here, heating circuit 1, 2, and 3, all have individual heating curves. So as the temperature outside is changing, all three supply wire temperatures are going to change simultaneously ongoing. So as the temperature gets hotter and colder, so too the supply temperatures on all three circuits are going to change simultaneously. In comparison to the next slide, let's have a look at. In this slide, rather than the reset mixing valves, we have the thermostatic mixing valves installed. And when you look at the heating curve on the top right, you'll notice that the blue and the yellow lines are not heating curves anymore. They are simply a maximum temperature. So the thermostatic mixing valves, these heating circuits, all three of them, are going to slide up the red heating curve until those individual heating circuits reach the maximum temperature that was dialed into the head of the thermostatic mixing valve. So you see the blue maximum temperature there is a horizontal line, so the inflow radiant system is going to run until we get to a temperature outside, and then that temperature is just maxed out on the blue line. It'll go no higher than the blue line as the temperature gets colder, but as it gets warmer, it stays on that blue line as well until it heats that temperature and slides back down the red heating curve. Our baseboard or cast iron system, slides up the baseboard heating curve as well until you get to the max temperature dialed into the thermostatic mixing valve, which is the horizontal yellow line, and that basically will be the max temperature allowed to go out to those particular systems. So if you looked at what those temperatures were, that yellow line is the max temperature that we need for our cast iron radiation at design temperature. So at -9, we needed about 61 degrees C. That's the temperature we dial into that thermostatic mixing valve for the cast iron radiation, 61 C. So once we hit that temperature on the baseboard heating curve, that's going to effectively energize that thermostatic mixing valve to maintain that 61 degrees C throughout the rest of the heating season as it gets colder outside. And the same with the blue line for the radiant inflow system, which is about 44 degrees C. Once the temperature hits that on the reset on the baseboard system, the thermostatic mixing valve for the radiant inflow system will now maintain that 44 degrees C for the rest of the time that we need to heat the building as it gets colder out. So looking back at the 3-to-1 rule I mentioned earlier in the presentation about dropping your supply temperature 3 degrees increases the efficiency, or basically the fuel, or reduces the fuel consumption by approximately 1%. Applying that to the using reset mixing valves versus thermostatic mixing valves, let's have a look at the differences in the efficiency of the different circuits based on outdoor temperature. So remembering back between about 12 degrees and 20 degrees C, we spend about 18% of the heating season in this area in Vancouver. We can look at the different heating circuits. So we wanted, based on that temperature, 12 degrees outside, we have a 38 degree supply temperature. With the reset valves, the heating circuit one's the same, 38 degrees, and we're actually going to supply 38 degrees C out to that high temperature circuit. The other circuits with reset, even though we're sending out 38 degrees to the high temperature, the mixing valve is going to drop that down to 34 degrees C for the cast iron radiation system. And in the heating circuit 3, it's going to take that 38 degree C supply temperature and mix it down to 28 degrees C when we use the reset mixing valves versus the thermostatic mixing valves. Looking over to the left with the thermostatic mixing valves, basically remembering that the valves are set to design temperature, we are not going to change that supply temperature at all. It'll go out at 38 degrees C to all three of those heating circuits, which means that we're sending more BTUs out to HC2 and HC3 than what they actually need. That's going to overshoot temperature in those. Remember, these are high mass systems, which means they absorb energy and they release it at a different rate, and which means typically you're going to overshoot temperature. Comfort levels will be impacted there. As well, we are using more BTUs than we need in a quicker rate. That's going to turn the boiler on, it's going to cycle more, and that's going to lower the efficiency of your system. So less comfort, lower efficiency. Whereas if we compare the 3-to-1 rule, when we use reset, those HC2 and HC3 would be somewhere between about 2 to 6% more efficient as far as their operation and also more comfort than the thermostatic system that we would install, which would be cheaper, obviously, as far as the cost goes to install it, but over time is actually going to cost the owner more money and actually have a little less comfort. So let's move on from there and have a look at the other temperatures as we get a little bit colder. Now, if we change to a little colder temperature, we spend about 50% of the heating season in Vancouver between about 5 and 12 degrees. And just taking that 5-degree operational temperature there, and based on the heating curve for HC1, we are going to send out 54 degrees C. HC2 and HC3 with the reset valves on them are going to meter down from 54 down to 44 and 34, whereas the thermostatic mixing valve system, again, they're all going to get the same temperature with the exception of the HC3. Now we have now hit the maximum temperature that mixing valve has been set to. So now we are at design temperature for HC3 when it is +5 outside. So we are typically sending out 44 degrees C water when it's -9 at design. We are there now at between about +5 and 12 degrees C outside. So you can see here that we are about 6% more efficient in our energy usage when we have the reset mixing valves at that particular temperature. So again, more efficiency, more energy savings, less wear and tear in your boiler, just equate to a better bottom line for your owner. And now between -2 and +5 in Vancouver, which is about 28.5% of your heating season. Again, you can kind of see and getting an idea here as we go through the different temperatures outside. As we are resetting, there is going to be, again, more energy savings and more comfort level in comparison to the non-reset mixing valves used when we have a thermostatic type of mixing valve system. The thermostatic mixing valves at this particular outdoor temperature are now set at design. So HC3 has been at design for a while now at 44 degrees C. It only needs 38, but it's getting 44. The HC2 only needs 52, but it's at 61. So it's at design now. And of course, HC1 is at 66. In comparison, the reset mixing valves are metering out the precise temperature, so obviously more comfortable still than the non-reset mixing valves. And you see a savings there as far as the operational efficiency of anywhere between about 3.5% to 5.5% on the reset side versus non-reset. So you can see from those previous slides that using the reset mixing valves adds more comfort as well as more efficiency. We're going to use less gas now to heat that building than we would if we had thermostatic mixing valves installed in that particular system. The other benefit is less wear and tear on the components in your system because there's less cycling of your boiler, which would mean less replacement, less repair of your heating system over its life cycle, which is going to save money as far as the perspective of the homeowner and the cost to operate that system over its life. So higher efficiencies, more comfort, and reduced repair and replacement costs are all benefits of utilizing reset on not just the boiler, but also on those mixed temperatures that we need as we add different thermal units to our heating system. In conclusion, thermostatic mixing valves. Obviously inexpensive, that's why they're popular as far as that initial cost. So if you have multiple temperature systems, people like to use thermostatic mixing valves strictly on the cost side. But as far as reset, they're not going to do that for you in your system. They're not going to add any of that outdoor reset capability. They're just strictly going to put a cap ceiling on that maximum supply water temperature. You dial in one temperature, and when that temperature is basically sensed by the valve, that's the temperature it's going to maintain. It's not going to go higher than that, but anything lower than that, there is no resetting. It just basically allows that temperature to go right straight through the valve and out to your system. And while reset mixing valves will be more expensive to install, there is a lot of value that is added to your heating system. There's a higher level of comfort, as we reviewed, less wear and tear on your components, more energy savings. So as these valves are in operation year over year, they're actually putting money back in the pocket of the owners of that particular building. So there is a great deal of benefit to adding these electronic reset mixing valves to your system. The benefit with a Viessmann system is that it's plug and play. There's not a lot of extra work you have to do other than just wiring and connecting the controls and devices in the system, and everything mates up and integrates together quite easily. So now that we've had a look at the differences between a reset mixing valve versus a thermostatic mixing valve, the increased level of comfort in the buildings using reset mixing valves, the increased efficiency of our system, energy savings year after year, less wear and tear on our components of our boilers, longer life cycle of our system as a whole, that we can relate this information to the decision makers and install more of the mixing valves that will reset versus the thermostatic style of mixing valve. I want to thank you for your time, and until next time, have a good day.